I hope your brains are a little bit more malleable now, if they haven't turned completely liquid after Marshall's talk there. As Andy said, I'm Richard Park. This morning I'm going to be talking to you about TamStat, which is a statistical package written using Dyalog. You can see we've done a little touch up on the TamStat logo there. so we're going to tame statistics using Thor's hammer today. Now, this isn't the first time that TamStat's been brought to a user meeting. If you go to dialog.tv, you can see these previous talks and see the development of TamStat since it was kind of introduced in 2014. But the creator, Stephen Mansour, he usually presents updates to TamStat, but he can't be with us this week because he's actually in Scranton using TamStat to help teach his statistics and business management course. So that's why I'm going to be talking about it today. I'll give a little introduction to TamStat and some of the motivations behind why it was developed, and then give you a little demonstration before Michael talks about some of the technical details of recent updates. So, all right, why another statistical package? This is something Stephen's talked about before, but the name TamStat comes from taming statistics, and that's inspired by Ken Iverson's idea of taming mathematics. So building a language with some consistent functions and syntax for mathematics. Well, that's what Stephen has done here with statistics in TamStat. And there are two approaches I want to sort of talk about in that regard. One is why use APL to develop a statistical package, and that's something I think the audience here will be really comfortable with, the idea that data sort of comes as arrays, and so using an array-oriented programming language to develop a statistical package is a fit that just sort of makes sense. But the other thing that I think makes TamStat sort of more unique and interesting is its use of operators. So in other popular statistical applications, something you might commonly want to do is find things out using probability distributions. And in those other applications, you'll usually have to sort of either autocomplete or search through a whole list of functions with somewhat related names to do some, to find some particular thing out. But in TamStat, each probability distribution is a single function, and then by applying operators, you create derived functions to find out what you're looking for. I'll make that a bit clearer by doing an example now. So many of you will probably have heard of Mensa, which is the High IQ Society. They have a published criterion for being a Mensa member, and that is that you take a standardized IQ test and you get a score that puts you at or above the 98th percentile. When you take an IQ test, you're going to get a score back, but you're not going to get like a pass or fail for Mensa, right? You need to go and find their criterion, okay, I need a score that puts me at the top 98th percentile, so then the question becomes, what IQ do I need? Well, let's tame the question using TamStat. So the IQ score that I need to qualify for Mensa would be the critical value, which comes from a probability distribution, where most IQ tests have scores which are normally distributed with a mean of 100 and a standard deviation of 15. And if I wanted to find out, the cutoff IQ score in Excel, this is what I'd have to do. I'd have to use the norm.inv function and then input my parameters like this. And already norm.inv is a little bit of an obtuse name, unless you already know that the critical value can be thought of as sort of the inverse of finding the probability from a distribution. The equivalent TamStat function, I think, is sort of much more human readable and much more closely resembles the problem statement. So the question we're asking here is, what is the critical value that puts me at or above the 98th percentile? And that's nicely reflected with the use of the logical function greater than or equal to. So you find that you need an IQ of 131 or more. And now we can sort of, all right, let's think about this the other way. Flip the question a bit and verify this, we're now going to ask, okay, so what's the probability that someone taken from the population has an IQ greater than or equal to 131? Now, again, in Excel, it's a little bit awkward because their equivalent function, norm.dist, in this example only tells you the probability that someone has a IQ less than 131, and then you have to do 1 minus that to find what you're actually looking for, which is about a 2% chance, a 2% probability. So this is sort of an example of the sort of, this taming statistics idea that I think makes TamStat pretty great. And it's kind of designed for helping people new to statistics, for teaching statistics, which is how Stephen uses it. But the issue can also be that if you're new to statistics, and if you're not particularly comfortable with programming, you might find learning the names of all these functions and operators and the order in which you need to put them to construct these expressions, it might be an extra barrier to your learning. So there was feedback from Stephen's students, and from that he developed a graphical interface for TamStat. Now there exists a desktop application, and it's a GUI version of TamStat, and you can push your mouse around and click menus, and then the application will build those expressions for you. But it only works on Windows, and some of Stephen's students use Apple computers. So it's been important for him to have a cross-platform graphical interface, and that's what the tools team at Dyalog have been helping Stephen to develop over the last couple of years. And it was originally in my server technology, although recently we now have HTML renderer and the Dyalog user interface, and that's allowing us to have a standalone application with a graphical interface that works the same and looks the same on all platforms. So I'll show you that now and use it to sort of build up the expressions from the example that I just gave. So when you load TamStat, this is what it looks like. You have a session, you can enter APL statements and TamStat expressions. You have some preloaded data sets that you can use to try things out. In the example, the Mensa example, we're interested in something about probability distributions. So we just go to the probability distribution wizard. And here you can see all of the probability distribution functions and the operators that work with those to find out different things. We were looking at what's the critical value, right, for our normal distribution, where IQ scores are distributed normally with a mean of 100 and a standard deviation of 15. And we're looking for the critical value that puts us at or above that 98th percentile. So when we run that, we get our IQ score back, 131, but we also get this graph from Chartplot, and it nicely highlights, all those scores which are, well, in green there, it's highlighting all the scores which are below a 98th percentile. And then we can also do our little inverse, so what's the probability that someone randomly selected from the population has an IQ of greater than 131? And there's our 2%. And now the highlighting is flipped to the other side, and that nicely kind of reflects the way that, we're sort of looking at two sides of this problem. We're just doing inverse operations here. There's one other example I'd like to quickly show you before I hand over to Michael. Something called confidence intervals. This just to demonstrate another one of the wizards. Confidence intervals, the idea is you've got a sample and you've got some measurements from a sample, and you want to infer something about the population as a whole, some true population value. So, for example, say I've got a class of 38 business management students and I measure all their heights. I can do a mean and standard deviation on that, but that only really tells me about the sample itself. The question is, can I find the true population mean height? And yeah, I'll let you see that twice. So in this case, we're trying to infer something about the population using confidence intervals. And most of the default inputs here are fine for our purposes, and we're just going to look at some confidence intervals for the height. And again, we get nice graphics. And this one, I think, sort of help to show things like, as our confidence level increases, then the range of our confidence intervals gets wider as well. So basically we're saying, okay, I have a 99% confidence that the true population height, based on 38 students from Stephen's class, is somewhere in this range between just below 67 inches and just below 71. Now, something some of the students might want to or might need to learn is, where do these percentages come from, and what is this confidence interval? Well, this confidence interval is also an operator acting on the mean function. Where do I get these numbers from? And we can build up this expression using other TamStat expressions in the session here. So I did have with me the TamStat guide, but in the TamStat guide, it gives you the sort of step-by-step how to construct a confidence interval. Let's build this up inside TamStat. So the first thing you need is an estimate of the mean. Well, let's go to the session and look at the data first. So the default selected data set is the student data set, and that's information from Stephen's class of 2016, things like, do you own a car, what color are your eyes, and we're going to be looking at the heights. So these are all of our heights. Now, I happen to know the function names. If you need to find them out, you can go to the summary wizard, and there's a list, there's a place where you can find lots of the summary statistics. But I'm just going to make a little train to find the mean and standard deviation of the height. The next step is something called the standard error, which has been defined here in terms of the standard deviation divided by the square root of the number of number of measurements. Although there is also a inbuilt function for that, so we can find the standard error. Afterwards, this is where those confidence levels come from, those sort of percentages come from finding the critical value from a t-distribution. So we just before found the critical value from a normal distribution. Let's do it for the t-distribution. And again, we're interested in probability distributions. This time it's the t-distribution, which is really similar, but it depends on the degrees of freedom, which are one less than the sample size. And we're looking for the critical value for less than a half of 1 minus our confidence level. So that's 0.025. It's not the probability, it's the critical value. And it's 0.025. Okay, yeah, so we're sort of highlighting the, okay, in between plus or minus this critical value is our 95%, which is where the 95% from the confidence interval comes from. Second to last is the margin of error, which is just that critical value times the standard error that we found earlier. So we can do this from the session. Now all the things from our wizards have come into the session. So we can find our critical value, and our margin of error is just that times the standard error of the height. And that's this here. And lastly, the definition of the confidence interval, which is the mean plus or minus that margin of error. So I can actually construct this quite nicely using a train, which is mean, minus, and plus. And then if I wrap this around, there's our 95% confidence interval. And you can see that's the exact same as if I do 0.95 mean conf int height. And notice how, even though I've constructed this train because I kind of know a bit more about it, I haven't had to use any APL symbols to construct it. All of the functions which do use APL characters are sort of wrapped in these named functions. If you do need to use APL in the session, you don't have a keyboard, there is a language bar available for that. One other quick thing before I pass on to Michael regarding this, which I thought sort of came out nicely with the graphs and the graphical interface, is if you find the confidence interval for the height, you get these nice symmetric confidence intervals at either side of our of our point estimate for the mean. But if you find the confidence interval for the variance, then you find that it's massively skewed to the right. And I didn't know why this was, and I asked Stephen. It turns out it's because while the critical value for, while the confidence interval for the mean is based on a t distribution, which is this sort of symmetrical bell graph, the confidence interval for the variance is based on a chi-squared distribution, which is massively right skewed. And that's why the confidence intervals are right skewed as well. So anyway, that's a little demonstration of TamStat in 2019. I'm now going to pass over to Michael, who is going to talk more about some of the technical details that went into implementing, especially the graphical interface there.
Yep.
Thanks.